all the way from the mighty energy technologies area. Please, ladies and gentlemen, give it up for Malavika Bagepalli.
Welcome to my house, baby, take control now. We can't even slow down. We don't have to go a while.
40 billion tons. That's the amount of carbon dioxide we all release in just a single year. And so scientists across the world are trying to capture and store carbon dioxide. Some of them are converting it into carbon black, a solid, stable form that's easier to store. But if we converted billions of tons of carbon dioxide to carbon black, we will have massive mountains of carbon just sitting there. How do we sequester, that is, take and store all of this carbon? One really good solution is to store it in buildings. Yes, millions of buildings are constructed every year, and on average, they last for more than 50 years. It's a perfect, large-scale, long-term solution. Hey, so what if we make a building material that doesn't only sequester carbon, but also is strong enough to replace steel and cement, which significantly contribute to carbon emissions? This is where my research comes in. I am developing carbon-sequestering composites. Think of composite as a nicely packed chocolate chip cookie, where instead of using flour, sugar, and butter, I'm using hemp from agricultural waste streams, carbon, of course, from the atmosphere, and lignin. Lignin is a natural polymer occurring in trees and also happens to be a waste product of the paper and pulp industry. So we compared our lignin-based composite with other such composites, and it was much more water resistant. That's great. But to ensure that it's strong and robust, I'm employing a science-to-system approach, wherein I'm performing fundamental analysis at the very molecular level and connecting my findings to the material performance at a more realistic scale. For instance, lignin has a very complex chemical structure that changes according to which tree it came from and how it's extracted. And to really understand how these differences affect material strength, I'm performing tensile tests and shear tests, which mimic the modes of failure from an application point of view. And by continuing to establish the structure-property relationships, I believe I can develop a strong material that will fit seamlessly in roofs, walls, and floors of our future buildings. And most importantly, sequester billions of tons of carbon dioxide.